Hi Madeline, this is Emily from Team 1. I'm doing my individual validation for you, and I'm going to start screen recording on my iPad, so hopefully you'll see it pop up over here somewhere. First item you wanted us to validate was item 3. So item 3, I don't know if my group realized it too, but when I went back to look at this, I realized that we didn't do it to your specifications. So I don't know if you want me to validate the work we did or if I get extra points for validating the work we didn't do, but I'm going to validate both just to attempt to get more points. But over here you just ask us to graph the function of the normal and tangent line. And then over here you say and label them with their equation. So we didn't label them with our equation. We did calculate their equations at some point, but the work got lost when we were shuffling papers. So all I had was our Desmos graph to go off of when I compiled all of our work to be more clear. So we did graph the function. We did do that first instruction. So what we went ahead and did was, the way that we graphed it was we plugged in the values that are given. So if you look here, we took the 1 and plugged it in for A, we took 0.1 and plugged it in for B, and we took 0.01 and plugged it in for C. Once we did that, we had a function of x, and we went ahead and graphed that in Desmos, and it gave us this strange little line right here. And you asked us to find the tangent and normal line at the point x equals 0. So the function crosses the y-axis where x would be 0, just under 10 here. And we drew the tangent line to that. So the tangent line, the formula for that, if we were to calculate the formula, which we didn't, unfortunately, you would just take the derivative of the original function that we have. So you would take this function, find the derivative of it, and then that would give you the slope for that line. Then you'd take the slope and you'd plug it into our x2 minus x, or y2 minus y1 equals slope x2 minus x1 formula. And that would help us get our actual formula for our x values and our y values and our slope. And that would be the equation for the tangent line. So derivative, plug it in, equation. Then to find the normal line, which we also graphed, it's perpendicular to the tangent line at that point. So it crosses through the exact same point right there. And it has a 90-degree angle to the other line. And a normal line's equation, its slope, comes from the equation would be the same as the tangent line, but it comes from the slope being the negative reciprocal of the original functions, the original tangent line. So the slope would be whatever was in the denominator becomes the numerator, whatever is in the numerator becomes the denominator, and the sign changes. So if it was positive, it becomes negative. If it was negative, it becomes positive. So negative reciprocal of the slope of the tangent line. Exact same equation, just with that slope in there. And that gives us a normal line. So that was that one all explained. This was a good one because it drew back to some of our first knowledge of the class that we learned with different tangent lines and what derivatives mean and that kind of stuff. So this was a good callback to all of that. And if we had done it right, it would have been a pretty straightforward question, which I appreciate. And then for item 11, we're asked to list the absolute extrema. So that's the absolute maximum and minimum of this graph you gave us. So for the graph, I just want to go back. I didn't show you our work for that last problem. Our work that we wrote out here was just a rough scratch work drawing of our graph from Desmos. So we looked at our Desmos and just quickly sketched it out so that we would know what to have for our scratch work. So there wasn't much scratch work to show, which is why I just showed the drawing. And same with this one, there isn't much scratch work to show. It's just a repeating of what's written in the box. So this has the graph, so I'm just going to show you this. Absolute extrema, our absolute maximum and our absolute minimum of the graph. Our absolute maximum is like the highest point on the graph that's represented, and our absolute minimum is the lowest point on the graph that's represented, like our y values that are highest and lowest represented. So here you can see that the lowest point is pretty straightforward. It's right here. It's going to be at y equals 1, and that is the lowest point on our graph. You can just clearly see that by looking at it. And then right up here, you would think that would be our absolute maximum or our highest point. But because it's an open circle, if you look really closely, I think, or we think, that it does not exist because there's no actual point there. It's just approaching that number, but it never really gets there. So at that point, it's undefined or something. There's nothing there. So we wrote does not exist for absolute maximum. And you could, if you were really pressed to get an absolute maximum, I'm sure you could put like limit approaching. No, it wouldn't be a limit. It would just be a number really, really, really close to that number, but not that number. Does that make sense? So you can never get close enough to actually say, like you could keep going decimals infinity and never really get there, which is why we said do not exist. So then you wanted us to validate, and that I like that problem because I feel like absolute maximum and absolute minimum wasn't something that we wasn't something we've explored too much. Like we did talk about it in class and it was on our worksheet, but it was nice to have a little revisit to it. And again, this problem kind of was tricky because of the open circle, so if we got that one right, then it was a good problem. I mean, it was a good problem either way, but that was that one. And it also, we had to, because of that problem, we had to call back to our local minimum max just to kind of know the difference. So you had to remember a lot of the things that we talked about. I think we didn't need any resources for this one, I don't believe. But it's something that even if you had Googled it and it Googled what an absolute maximum and minimum is, you still would have needed to take the time to understand it so that you could figure out what this one was. So, good problem. Liked it. I don't know why I'm giving you a review of every problem. I probably don't need to do that. Item 16 is the next one you want validation for. In 2 to 3 sentences, explain the mean value theorem in your own words. Accompany your explanation with a visual of MVT. So, I don't know if you want me to explain this in my own words again, or if I should just read it off. I don't want to just read off my work to you. I feel like that's not helpful for validation. So what I'll do is I'll show you the drawing and explain the drawing in my own words. So, mean value theorem applies to any continuous and differentiable curve line situation function. That's the word. So I just drew I guess that would probably be a sine curve. I just drew a random curve to represent it. And you're given an interval between like A and B. Looking at this interval, there are 2 points on the interval, point A and point B. So we're labeling the same. Point A and B is their interval. Anyway, if you have these 2 points on a curve, and you drew a secant line between them, the slope of that secant line will be equal to the slope of a tangent line at a point somewhere in between A and B. So you can see that in our drawing here. Here's A, here's B. and falling somewhere in between it is C. And at C, the tangent line has a similar slope, or exact same slope, a parallel line to our secant line. And this is just because, like, I mean, it's kind of logic. If you just think of a linear line, like a completely straight line, the slope of the tangent line is always the same, right? Because at every point it's traveling at the same speed. But if you take two different points, wherever they're oscillating, does that make sense? Oscillating? Is that the word I want to use? If there's 2 points, there's going to be a center point somewhere. It doesn't have to exactly be the center, but there's going to be a point somewhere in between them where the slope of the line is the same. I don't know how to draw this to show you. Ooh, that's the wrong one. Ooh, okay. So if I take, even if this point, like say point A was up here and point B was down here, and there was a secant line between them, there would still be a point somewhere over here where there's a tangent line. So as these two oscillate, so this one moved this way and this one moved this way, as they oscillate around each other, there's always going to be a point in between where it's so smart, don't you think? I don't know. I think it's cool. Because it makes sense when you think about it, but a lot of things in math don't make sense when you think about it, so I just like this. And that was our drawing of it, and that was our explanation, basically. Okay, so for item 18, which you asked us to validate, it's the second part to the problem of drawing drawing out the problem. So what you want us to do is determine and provide the definite integral that represents the area of the bounded region. Do not integrate it. So this, again, was pretty straightforward of a question because we already had the drawing done. I'm going to erase some of this work. Ooh, I don't know if I can. Anyway, when we look at the thing that we've drawn, our left bound and our right bound are really easy to fill in on our integration. So our right bound is x equals pi, our left bound is x equals pi halves, and you can see that really clearly right here. And it was just listed up here, that's how we got it. So when you're writing it out in integral, that's the form that you use. You put the right bound on top and the left bound on the bottom, so that's what we did. And then it's just the bottom curve, which is sine x, and the top curve, which is f of x equals x. So the area between those, you would put the bottom curve subtracted from the top curve, because it would be the integral is the area under the curve, and we just need the area under the curve of between two curves. Does that make sense? So instead of taking just sine x, or just x, for example, then we would just get, I don't know how to explain this without showing you. Maybe I can draw it out. So if we have, say, so this is our top curve right here, and this is our axes. If we just took the integral of that top curve, all of this area down to the x-axis would be filled in. But we want to subtract the area under the second curve. So the bottom curve, if we were just to take the integral of that, we would just get this area right here filled in. But we want the area in between. So if we take that area right there and subtract it from that big area from the top curve, we just get what's in the middle, in between the two curves. Does that make sense? Makes sense to me. Anyway, so this was a really good problem because it was more than just our basic area under the curve. We had to remember how to do in between two curves. So that's our bounded region. The area that's shaded was the integral 2 bounds of the area under the curve of the first top line minus the area under the curve of the second bottom line. So that was 18. Then you asked us to do, okay, so for item 19 and 20, you wanted us to validate both of them. So you ask, a slight change in integrand will determine the technique of integration. So explain the difference between the two integrals that demand control the integration technique that you'll use. And then your goals will always be to transform the non-basic form integral into a basic form integral. Even in integration by parts, your second integration should be at best a basic form integral. So what I went ahead and did for this one was we wrote out the explanation first. So we said integration by parts is used for the x cosine x dx because the derivative of x squared negates x and turns cosine x squared into a basic form. Integration by parts is used because the derivative of x won't cancel out our initial x and we will be stuck with the same problem. Because there is no other way to turn this into a basic form, we must use integration by parts. So, in short, one of them cancels out into a basic form and one of them doesn't. And the one that doesn't, you need to use a different method to try and get to the basic form. So that's kind of how I think of it and the process I use to get to it. So we'll see in our work how we did that better, but I just want to show you what our answers were. So the name of the integration technique is integration by substitution for x cosine x squared. And the basic form of it is 1/2 integral cosine u du. And then the name of the integration technique for x cosine x is integration by parts, and it gets you to the integral x sine x minus integrand sine x dx. So I'll show you our work for that because me just saying that means nothing. This wasn't a problem that I worked on, so I'm not sure I'll be able to follow our work super clearly, but you can see for integration by substitution, which one was substitution? Yeah. For integration by substitution, we substituted out one of our variables to be u. So we made u represent x squared, and du represent 2x dx, and dx represent du over 2x. So we take x cosine u equals du over 2x, because we're filling in where the x was. And then we can go ahead and plug back in our 1/2, which gets us rid of the 2 in the du dx. So then it's just du over x, and there's already an x over there, so those cancel each other out. So it becomes cosine u du times 1/2 integral. So I don't know how to say that in words. 1/2 integral cosine u du. And then for our integration by parts, we did x cosine x dx, and again we make u represent our x, u represent our sine x. U represent our sine x? Oh, because the opposite of cosine x is sine x. So du equals dx, du equals cosine x dx. So we can go ahead and put it into parts of x cosine x dx equals x sine x minus integration sine x dx. And that works because you're just inversing the product rule, basically. So you know how in the product rule, you multiply one by the other. I don't know how to explain this in words. In the product rule, you're taking everything multiplied by itself. And that's why it's called product, because multiplying something by something equals product. And you're just reversing that. So you go from one, in product rule, you go from two values down to one value. And this one, you're going from one value to two values. Does that make sense? And that's why you get x sine x and then sine x dx. Because, yeah. Okay. So that was my part 1. I'm going to go to another video for part 2. Okay, so for validating part 2 of the exam, you asked us to take item 1 and just exercise 21. So we have to rehash our discussion on these problems, declare variables and parameters used in these instances, and then summarize what you discovered and learned in each of these exercises and relate your learning to specific ideas about limits and derivatives and the process of using limits and derivatives to answer questions. So I didn't show our work for these problems, like our actual scratch work for how to solve these problems, because I just explained it in words and discussed what, summarized and discussed what we learned in each of these exercises instead, because that's what you asked us to do. So you told us not to copy our notes. So for item 21, I'll read you what I wrote, and then I'll go in and add some things in as we go. So in item 21, we were in section 3.7, which was rates of change in the natural and social sciences. So these were like applied problems for us, even though we obviously had play and apply problems. I'm pretty sure this was a play problem. They all were actual application to physics or architecture or science. And we were trying to learn to differentiate or find rates of change using the definition and rules on functions on applied problems about science. So here we were given that the rate of change of a constant equals a constant, and that the rate of change of velocity is acceleration. So from d over dt mv, we can assume that f equals ma, but we are given a function that represents the relationship between mass and velocity. That same formula given in 46, we prove through the same formula that's given in 46, we prove that if f equals ma and m equals m naught over square root 1 minus v squared over c squared, then force equals m naught times acceleration over 1 equals v squared divided by c squared to the 3rd. Using quotient rule and chain rule to differentiate mv, which is a force. Once we do that, we can replace dv dt with with acceleration like stated in the question and prove the force in theory of relativity equals that of the equation. So that was really wordy and hard to follow. So I'm going to show you the actual equation to try and explain it better. So here we are given that force equals the derivative of mass times volume. Mass is a constant. The derivative of a constant is a constant. So mass stays the same. It's just going to be the derivative of mass is mass. Velocity, on the other hand, the derivative of velocity is acceleration. So it can be rewritten as force is equal to mass times acceleration. And acceleration equals dv dt. But in theory, so again, the derivative of velocity with respect to time. But in theory of relativity, the mass of a particle varies. So in theory of relativity, that mass isn't constant, so you need something else to represent it. And that mass varies with your velocity as follows. So they give you an equation that is the kind of gateway between velocity and mass. So mass depends on velocity, so this is the formula for how they're related. So you can see that mass equals m naught divided by, which is a constant, divided by 1 minus v squared, which v is what's changing, divided by c squared, which is speed of light squared, and that is our a constant again. So I forgot to declare variables. They're on here, but I forgot to declare them just now, so I'm going to go ahead and declare them. Capital F is force, lowercase m is mass, m0 is m naught, which means mass at rest, v equals velocity, c equals speed of light. Those should be all the things we need to declare. So once you're given that formula of how velocity relates to your mass changing, we can go ahead and show through those formulas that this formula is true, because we're using the force MA formula up here, and we're using this formula right here. So we can say m naught times acceleration divided by 1. So like it's all of the work that I showed back here. I'm having trouble explaining it right now, but use quotient rule and chain rule to differentiate mv, which is force. So you take the derivative of mass volume, mass times velocity. Once we do that, we can replace the dv dt, because you get the derivative of it, with this. I'm having a moment. You can replace the dv dt, which is the derivative of velocity with respect to time, with acceleration, because the derivative of velocity is acceleration. So once you do that, it's stated in the question, and you prove that all of those formulas relate back to this formula right here. And once you've done that, you've proved the problem. So that helps us just understand kind of the application of how these types of problems would work in the real world. It's a rate of change, like as the rate at which velocity changes affects how the rate of which mass changes. And rate of change is your integration. Is your derivative. The rate of change is your derivative, and your derivative represents the rate at which something's changing. So the rate of change of velocity is related to the rate of change of mass. And so you can go ahead and snake all those problems around to prove that formula. And it's an actual useful formula for people who are trying to calculate the mass of objects that are moving really fast, and how those change in the theory of relativity. So that was pretty cool. I liked that. You asked us to validate item 2 in part 2, parts F, G, H, and I. So here it is, item 2. We're given that the acceleration is in meters per second squared of a particle moving along a line in a rectilinear motion, and it's given by a function where v is the velocity in meters per second and t is the time. So we already got the first few parts done with our team validation, and now we're hopping into part F. So the first thing you asked us to do was draw a diagram to represent the motion of the particle, include the time and the corresponding position, and the direction of travel indicated by the arrows. So we've drawn you a motion diagram on an exam before, and I don't think we did it to what you wanted for your specifications, so we had to go ahead and adjust our method. I'm still not sure if it's exactly what you were looking for, but we tried our best. So our little axis is our time, and we gave you little notes down here that our arrow size corresponds to our velocity. So the longer the arrow, the longer the velocity, or the bigger the velocity. And no arrow equals no velocity, meaning 0 at rest. The particle's at rest, there's no velocity. So you can see that at 0 time, it is moving with large velocity towards 1, where it's moving with less velocity, and then it comes to a rest at 2 seconds, and then it's moving in the opposite direction slowly with less velocity, and then it's moving in that same backward direction with more velocity, and then it's slowing down again, but still going in that same direction. Then at 6 seconds, it comes to a rest or a stop, and then it moves in a different direction at 7, moving forward again, slower, less velocity, moving forward with more velocity at 8. So I don't know how to explain this. It's more of a visual representation, which you can see on the screen. But we did this by all of the calculations we did up here. So up in the earlier parts of the problem, we had already determined that the particle is at rest in 2 and 6 seconds. So those were easy to fill in. We just filled them in with dots. At 2 seconds and 6 seconds, there was no velocity, so 0. So dots. Before the particle is at rest, it's moving in one direction, while after it's moving in a different direction. So we, in part E, calculated that the particle is moving, or figured out that the particle is moving forward when the velocity is positive from 0 to 2 seconds. And then after, from 6 seconds, it's also moving positive, so from 7 and 8. And then in between, it's moving in a negative direction. So we figured all of this out before, and we knew that at 1, 3, and 7, we had different velocities where it was slowing down or speeding up. So that was F. For G, you asked us to find the position of the particle at time t. So position is going to be the integral of velocity. So integral is just the opposite antiderivative. And when you take a derivative of position, you get velocity. So you can reverse that process to get position from our velocity using our integration. Okay, so once we go ahead and take the integration of velocity with respect to time to get position with respect to time, it just goes ahead and normal integration with plus c at the end, and then we can go ahead and plug in p of t as t cubed minus 12t plus 36 plus c. And once we have that, we can solve for p of 0 equals 0 to calculate our c. So we went ahead and set the equation equal to p of 0, which is 0, and plugged all of our t's in at 0, and that gave us c is also 0. So c can kind of be erased from the problem, and that gives you the formula pt equals t cubed minus 12t squared plus 36t. So that's how you get the formula for position from your velocity function. And that just used the integration technique that we learned in class, but applied to this problem. So then you asked us to find the total distance traveled by the particle using the first 8 seconds. So again, we used the total distance equals integral ut. So from our bounds of our integration are 0 and 8. So on the left, time equals 0. On the right, time equals 8. It looks like a u, but it's a 0. Yeah, it's integration. It's integral of 0t, not ut. So we plug in that original velocity function that we have, the 3t squared minus 24t plus 36, and we get the integration of it, which is the other formula that we have, which is t cubed minus 12t squared plus 36 plus 0 with regards to 8. And we plug in 0 for all of that, minus 8 for all of that, because again, the total distance traveled would be the position at 8 seconds minus the position at the position at 0 seconds minus the position at 8 seconds. And that goes ahead and gives you 32 meters is how much is totally traveled overall. So it goes back and forth, but you need to. And then for part I, it says in the first 8 seconds, determine when the particle speeds up and slows down. Explain how you know the particle is speeding up and slowing down. So, the particle is slowing down when the velocity and acceleration are different signs. From 0 to 2, velocity is positive while acceleration is negative, so it's slowing down. From 2 to 4, both are negative, so speeding up. And from 4 to 6 seconds, acceleration is positive and velocity is negative, so slowing down. From 6 to 8 seconds, both are positive, so they're speeding up. So this was just basic looking at the velocities and the accelerations and what their numbers were. We also, I think we might have graphed this to help us in Desmos, if I'm remembering correctly. So looking at it on Desmos, you can also see when the values are positive and negative on both of those lines. So that makes it easy to look at too. I'm approaching my time limit, so I'm going to be quite quick with this last section, but it should be fine. You ask what most impacts your persistence, confidence, and or enjoyment in any class. I think this was something that we talked about in our very first discussion. I'm really impacted with how professors treat you. Like if I'm one of those people who's really well motivated by trying to please someone else. I'm a people pleaser. So if I like my professor and want to do well for them and I've built a relationship with them, then I don't want to let them down. And I want to push harder and make sure I submit assignments on time and stuff like that. So that definitely impacts my persistence and confidence and enjoyment. But also, I appreciate when professors give you time to think. They give you time to organize your thoughts and be wrong with your thoughts before they want just a right answer and want to criticize you for it. So that's always positively impacting when professors give you a chance to be wrong and give you a chance to compile your thoughts and just talk things out. And then what can be improved to increase the positive impact of any STEM class to your persistence, confidence, and enjoyment of the class? I really liked a lot of the things we did in this class, like teamwork and take-home exams, and I liked your approach on this last exam to open resources. I think all of those are things that should be incorporated into STEM because, I mean, if we're being real with ourselves, there's not going to be a situation where we're calculating the integral of something and not able to look up what an integral is. Like, we always have access to Google unless we're out doing like field work or something like that. But in that case, you would have researched and maybe brought other different resources to help you. So I just think that your approach to that for the final exam was really helpful, and I think that would be helpful in other STEM classes. Like when you go into an exam and they're like, no calculators. And I'm like, when are we ever without a calculator? Like, you know what I mean? Like I always have one in my pocket with my phone. And if you were in an office job where you needed to calculate things quite often, you'd always have a calculator. And if you had something where you have a graphing calculator or a calculator that does it for you, of course you'd have access to that, like if that's your job. So I just think those types of things can be really helpful, and that's what I'd implement is more open resource exams. Maybe not like, I don't know. Yeah, I think that would be really helpful. And then, and it would increase my confidence too. Like, I dislike when professors will put you on the spot for something. Like they'll flash a problem up on the screen and then say, okay, I want answers. It's like, I don't have an answer for you yet. I just looked at the problem. But if you were asking what I thought of the problem, I could talk about that. So I liked how you approached that with our class, with having us talk out our thoughts with our groups and things like that. And I think group work would be really helpful too, because most of the time you're working on a team, and I feel like a lot of STEM majors don't have great interpersonal skills, so we don't work very well together. So I think STEM majors working on more group work would be really, really helpful and would impact my enjoyment of the class, because I like working with other people. So those are the things that I would improve. Thank you for a great class. It was really awesome. It was a great semester.